Welcome back to another classical mechanics lecture, and in this video we're going to begin talking about oscillators. Now this topic is one of the more important topics of this class for two reasons. Firstly, oscillators show up everywhere in physics, and secondly, almost every system in the universe can be modeled as a harmonic oscillator. What do I mean by that? Well, let's do an example to demonstrate it. So let's consider a mass m, and let's say it's subjected to a force who has an associated potential function given by u naught over 1 minus x squared over r squared. Now, what does this look like? Well, if we were to plot this, then we're going to see this parabolic shape that's at a height of u naught. We want to solve this system, but this potential is very confusing and a little complicated. So instead, what we're going to do is we're going to displace our mass a little bit to one of the ends of our potential well, and we're going to observe what happens when we let it go. And what's going to happen is the mass is not going to have enough energy to escape the potential well. Instead, it's going to sit here and oscillate back and forth about the minimum. And so we can model its potential as a harmonic oscillator potential, which we saw in the last video is 1/2 kx squared. And you can remember from intro physics that k over m is equal to the angular frequency squared, which we'll derive in a little bit. So we want to be able to model our potential as a harmonic oscillator by pushing or displacing our object from equilibrium, just slightly. Well, how do we do that? Well, we need to Taylor expand our potential function about equilibrium. Where is equilibrium? Well, clearly equilibrium in this graph is x is equal to 0. So we're going to Taylor expand about x is equal to 0. Well, u of x is u naught times 1 over 1 minus x squared over r squared. The Taylor expansion for 1 minus u is equal to 1 plus u squared plus dot dot dot. So can we use this Taylor series expansion? And this is something that's important to check. We need to replace u with x squared over r squared. And is this valid? Well, as u goes to 0, x also goes to 0. So this is a valid Taylor series expansion. It's important to check that. So using this, we can actually approximate the parentheses in here as 1 plus x squared over r squared. And we don't need to add any more terms because we're trying to match this potential function or approximate it with 1/2 kx squared, something that is quadratic. So we have a quadratic term here, so we don't need to go any further. All right, so writing down conservation of energy, we have the kinetic term, 1/2 mx dot squared, plus our potential term, which is u naught plus u naught over r squared times x squared. And this is going to be approximately equal to a constant. Well, this term right here is an approximation, not the full potential. Right, well, u naught is a constant, so we can subtract it over to the right-hand side, and we have 1/2 mx dot squared plus u naught over r squared x squared is equal to a constant. We'll just call constant. Now, we said that this potential right here is going to approximate a harmonic oscillator. So we have 1/2 kx squared should be equal to u naught over r squared x squared, which tells us that the spring constant k is going to be what? 2 u naught over r squared. Or in other words, k over m square rooted, which is equal to omega naught, is going to be the square root of 2 u naught over m r squared. So what we have just done is we took this potential that's complicated and we Taylor expanded it out to second order and we approximated it as a harmonic oscillator. In other words, we took our mass and we displaced it a little bit from equilibrium and we observed its motion as it oscillates in this potential well around equilibrium. And it's going to oscillate with an angular frequency given by omega naught. So we understand this system simply by approximating its potential as a harmonic oscillator. This shows up everywhere in physics. For example, the bonds between atoms can be approximated as a harmonic oscillator. All right, so let's go ahead and start talking about the most general oscillator. So let's assume we have a mass that's connected to a spring. The mass is m, the spring stiffness is k, and let's say this spring is at rest at x naught. So this is its equilibrium position. In other words, at this position, the mass is not experiencing Hooke's law. And then let's displace it by an amount x minus x naught. So we displace it to a point x. We're going to subject this mass to three forces. Firstly, 1/2 k x minus x naught in the x hat direction. Note that if x naught were to be equal to 0, so x naught is the origin, its equilibrium position is the origin, then this force just becomes a minus kx in the x hat. The second force we're going to subject it to is drag. So the force of drag is minus lambda v from a couple videos ago, which is minus lambda x dot in the x hat. And the third force is going to be some external driving force, which we'll talk about a lot more in the next video. Writing down Newton's second law, we have mx double dot is going to be equal to minus lambda x dot minus kx plus f external. We can divide by m and rearrange, and we're going to get x double dot plus lambda over m x dot plus k over mx is equal to f external. We're going to define 2 beta, where beta is the drag coefficient, to be lambda over m. And we're going to define omega naught squared to be k over m, the natural frequency. So we get the most general equation of motion for a harmonic oscillator, which is x double dot plus 2 beta x dot plus omega naught squared x is equal to f external. And in this video, we're going to look extensively at what happens when our driving force is equal to 0. So when the driving force is equal to 0, this is called a free oscillator. And the equation of motion is x double dot plus 2 beta x dot plus omega naught squared x is equal to 0. Now to solve this differential equation, what we're going to do is guess that x as a function of time is going to be written as some exponentials, or a pair of exponentials, because this is a second order equation. Plugging this in and dividing out by e to the rt, we're going to get r squared plus 2 beta r plus omega naught squared is equal to 0. Now, we have to stop here because the oscillator is going to behave differently depending on what the damping coefficient is. So we have three cases. The first case is when beta is equal to 0. There is no friction. And when this is true, we have r squared plus omega naught squared is equal to 0, which tells us that r is plus or minus I omega naught. And so we can write x of t as a constant e to the I omega naught t plus another constant b to the minus omega naught t. But we can write this in a slightly more suggestive way by noting that e to the I theta is cosine of theta plus I sine of theta. So we can write this as a times cosine of omega naught t plus I sine of omega naught t plus b times cosine of minus omega naught t, which is the same thing as just omega naught t because cosine is even, minus I sine of omega naught t because sine of minus omega naught t is just minus sine of omega naught t. Now we can group our real and imaginary parts, and this is going to be equal to a cosine of omega naught t plus b cosine of omega naught t plus I times a sine of omega naught t minus b sine of omega naught t. We're going to factor out a cosine, and we're going to get cosine of omega naught t times a plus b, and then we're going to factor out a sine of omega naught t. And this is going to be sine of omega naught t times I a minus ib. We're going to define a plus b to be a new constant, a tilde, and ia minus ib to be a new constant, b tilde. And so x of t really can be written as a tilde cosine of omega naught t plus b tilde sine of omega naught t. And it's okay to define a and b as we've just done because I is just a number and a and b are also just numbers. So we're just redefining numbers to be numbers. So if we have no friction, then our oscillator is just going to oscillate for all of time, which should make sense. All right, and in the second case, case 2, we're going to have overdamped friction. In other words, beta is going to be larger than omega naught. And what's going to happen is that our oscillator is actually not going to be able to oscillate. Its solution is just going to decay in time because the friction is very strong. It's just going to slow down our oscillator. So we have r squared plus 2 beta r plus omega naught is equal to 0. We can use the quadratic equation to solve this. We're going to get r plus and minus is going to be equal to minus 2 beta over 2 plus or minus the square root of 4 beta squared minus 4 omega naught squared divided by 2. We can factor out the square root of 4 and that becomes 2. So this becomes minus beta plus or minus the square root of beta squared minus omega naught squared. And now you can see why we defined 2 beta to be lambda over m because it helps us factor out this 4. Now, so this tells us that our solution x of t is going to be a e to the minus beta plus square root of beta squared minus omega naught squared times t plus b e to the minus beta minus the square root of beta squared minus omega naught squared t. We can factor out the e to the minus beta, and this becomes e to the minus beta t times a e to the square root of beta squared minus omega naught squared t plus b e to the minus square root of beta squared minus omega naught t. Because beta is larger than omega naught, this term out here is going to dominate. So we see that our solution is just going to decay in time. And graphically, what this looks like is, well, our solution is not even going to oscillate. There's no sines or cosines or complex exponentials here. So instead, we're just going to have a sort of decaying exponential. So you can imagine our spring just kind of like slows down as it's being drawn out or drawn back in. No full oscillation. Now the third case, which is the most important case for this class, the one we're going to deal with the most, is the underdamped case. Here, our solution is going to oscillate, but they're going to be decaying oscillations. And beta is going to be less than omega naught. So we have r squared plus 2 beta r plus omega naught squared is equal to 0. So r plus minus is going to be minus beta plus or minus the square root of beta squared minus omega naught squared. However, the inside of this is going to be negative because beta is less than omega naught. So if we factor out a minus 1, this becomes minus beta plus or minus I times the square root of omega squared minus beta squared. all I've done was to factor out a square root of minus 1, which is I. So our solution x of t becomes a e to the minus beta plus I square root of omega naught squared minus beta squared plus times time, be to the minus beta minus I square root of omega naught squared minus beta squared times time. Factoring out an e to the minus beta, x of t is going to become e to the minus beta t times a e to the I square root of omega naught squared minus beta squared t plus be to the minus I square root of omega naught squared minus beta squared t. Now we're going to define omega to be the effective frequency, which is the square root of omega naught squared minus beta squared. So x of t is e to the minus beta t, and as we've just seen, we can rewrite this as a tilde cosine of omega t plus b tilde sine of omega t. So we get oscillations that are decaying in time. And graphically, what this looks like is we're going to start with some oscillations that are just decaying in time. So here's e to the minus beta t. One thing to point out, that if beta were equal to 0, then omega, the effective frequency, is just square root of omega squared, which is just omega naught. And so x of t is going to become what? Well, the exponential goes to 1, so we're going to get a tilde cosine of omega naught t plus b tilde sine of omega naught t, which is exactly what we saw in case 1. All right, so I encourage you to go through some examples of working with different oscillators on your own. There are many in Taylor's classical mechanics books of these types of problems, so I encourage you to work through them. And in the next video, we're going to look at what happens when we introduce a driving force, a constant and non-constant driving force.